Welcome to this explainer. Look, if you're a computer science student, a networking nerd, or honestly just someone who absolutely loves pushing old hardware to its limits, you are in the perfect place. Today, we're diving into a step-by-step systems design. We're going to take some heavily constrained mobile Linux hardware, specifically Ubuntu Touch, and transform it into a powerful multi-node local network. We're going to build a completely local web server and a reverse proxy right from scratch.
Think about this for a second. What if you could build your very own private version of YouTube or WhatsApp, running completely on a single Wi-Fi network, using nothing but open-source tools? Imagine grabbing those dusty Ubuntu Touch devices sitting in your drawer and turning this into the ultimate engineering challenge. We're not just, installing an app here. We are architecting a fully private, localized internet ecosystem right in your dorm room or living room.
So, here's the game plan. We'll start by setting up the entry server. Then we'll look at routing traffic across devices. After that, we'll get into building dynamic backend logic, creating mock local services, and finally, we'll cover some crucial network constraints.
All right, part 1, setting up the entry server, laying the foundation.
We have to start with the bedrock of our network, getting that primary device configured. But right out of the gate, we hit a major boss battle. If you've messed with Ubuntu Touch before, you know it uses a read-only root file system. Now that's fantastic for mobile security, but it's a total nightmare for systems engineering. It literally means you can't just pop open a terminal and run a standard apt install nginx command. The system will just reject it outright. So how do we actually fix this?
To get around this massive roadblock, we use an incredible native tool called Libertine Containers. What Libertine does is spin up this secure, Chroot-like read-write environment right there on the device. By jumping into this container, we completely bypass the host operating system's read-only restrictions. It lets us install pretty much any standard Linux package we're going to need for our server.
Here is the exact 4-step playbook you'll follow. First off, install Libertine straight from the Open Store. Second, open your command line interface and create your container, usually with a command like libertine-container manager create. Third, you execute into that container's bash shell. And finally, step 4, inside that brand new read-write environment, you can actually run apt update and apt install nginx. Just like that, you've got a web server environment running on a completely locked down mobile device.
Now, a quick note on our port selection. Notice we're configuring nginx to listen on port 8080 rather than your standard HTTP port 80. Why is that? Well, in Linux systems, binding to ports under 1024 generally requires root or superuser privileges. And honestly, trying to navigate root access inside a containerized mobile environment gets incredibly messy and can completely break confinement. By sticking to port 8080, we avoid root altogether. It keeps things so much simpler and secure. You just grab the device's local IP, punch it into another device with :8080, and boom, your nginx welcome page is live.
Moving on to part 2, routing traffic across devices. This is where we build the reverse proxy.
Okay, having one web server is cool and all, but a distributed network? That is where the real computer science fun kicks in. In our target topology, we have our primary entry point, device A. This acts exactly like a traffic cop, running an nginx reverse proxy, listening on port 8080. Then we have devices B and C. These are our application servers, the ones actually holding the content, like our mock YouTube or WhatsApp. The user only ever talks to device A, and then device A silently works behind the scenes to fetch the requested data from B or C on their behalf.
To turn device A into that smart traffic cop, we have to set up specific routing rules in its nginx configuration. So, if a user on your local Wi-Fi visits the URL path /YouTube, nginx catches that request and proxies it directly to device B's IP address. If they hit /WhatsApp, it proxies it right over to device C. nginx is totally the industry standard for this for sure, but if you're just experimenting, you could absolutely swap it out for lightweight alternatives like Mitmoxie or TinyProxy inside your Libertine container.
All right, part 3, building dynamic backend logic. Let's talk smart request routing.
Static routing with basic URLs gets the job done, but let's level up our engineering here. Instead of forcing users to type out rigid URLs like /YouTube, we can build a super clean front end right on device A. Picture this, a single web page built with vanilla HTML and a tiny bit of JavaScript, and all it has is a simple search box. The user types a specific search term in and hits enter. The moment they hit enter, a backend script, let's say we built it in Python using the Flask framework, intercepts that input.
This is where the magic happens, with some intelligent if-else logic. The Flask script actually analyzes the query. If the text contains the word video, Flask dynamically makes an HTTP proxy request over to device B. If it sees chat, it routes the request to device C. It fetches the response and seamlessly hands it back to the user. You've basically just turned an old Ubuntu touch phone into a highly intelligent load balancer and API gateway.
Section 4. Creating mock local services. Time to build those actual destinations.
So with our complex back-end highways totally paved, we actually need to build the destinations that devices B and C will serve up. Since our private network is completely cut off from the global internet, we obviously aren't running the real YouTube or WhatsApp platforms. Instead, we'll use open-source tools to build local demo pages that functionally mock them. Device B could host our mini YouTube, just a web page with an HTML5 video player streaming MP4 files stored right on the device. Device C could host a real-time chat interface powered by WebSockets, letting two people on your Wi-Fi text each other instantly. You could even spin up a mock Amazon page utilizing some CSS templates and static e-commerce product data.
The really crucial takeaway here is our complete tech stack. If you're documenting this for a computer science project, this setup is basically your holy grail. It perfectly summarizes the open source tools running our localized architecture. Libertine handles our containers, Nginx handles the web server and proxy routing, Python Flask does the dynamic backend thinking, Node.js with the WS library powers the real-time chat, and vanilla HTML and JS handle the user interface. Every single piece is open source and entirely self-hosted.
Finally, Section 5. Crucial network constraints. We need to ground this architecture in reality.
As amazing as this system sounds on paper, before you go and deploy it, we have to talk about real-world networking hurdles. These will absolutely break your setup if you ignore them. First off, you have to make sure your home Wi-Fi router actually allows device-to-device communication. Some routers have a security setting called client isolation turned on by default, which literally blocks devices on the same network from talking to each other. You have to turn that off. Second, and this is absolutely critical, you must set DHCP reservations in your router settings. Because if device B reboots and grabs a brand new IP address, all those static proxy routes on device A will point to a dead end, and your entire network fails. Also, keep in mind, these are phones, not enterprise server racks. Expect hardware limits on battery life and concurrent user capacity. And remember that all of your configurations have to happen inside that Libertine container or via SSH because of Ubuntu Touch's